This is what we started learning last time, filter design, that how we actually go and design a filter, and part 3, filter design techniques. And there are 3 types of filters: low pass, band pass, high pass. There could be several, like band stop filter and notch filter, and you can find several, but there are 3 main categories of digital filters. And then I talked about FIR versus IIR filters, that given specifications you can either design FIR or IIR filters. This is an example, and this is how the specifications are given. That usually delta 1 is given. Delta 1 means the tolerance, the passband tolerance. Then a transition band is given where the frequency response will drop down to small value. This is delta 2. So this is called the transition band. And then you need to specify the stop band attenuation, that how much you want the frequency response to go down in the unwanted band. Usually it is given in dBs. So it's 20 log base 10 delta 2. So delta 2, if it is in terms of power of 10, so that will be multiplied by 20. So 40 dB means 100, 1 over 100, and 60 dB means 1 over 1000, and similarly 80 dB means this or that. So this is how the specifications are given. Usually it is plotted in dBs. So this is a dB plot, the specifications. And then this I showed last time, that this is how the specifications are either given in analog domain. So capital omega means the analog domain and the sampling frequency, and then you convert it to discrete domain with simple relationship that capital omega, small omega is equal to capital omega into t. So you can convert specifications analog domain to digital domain. So we covered this. Then I mentioned about the IIR filters, that IIR filter design is done using analog filter techniques. So you design these filters in analog domain, and with the techniques already exist. So analog IIR filter design methods have simple closed form solution, one reason for doing this. And the second a very compelling reason is that design examples have existed for years. So we make use of those design examples. So usually they are not designed in direct in digital domain. So direct design of FIR filter is obviously possible. Then I covered this, that you have discrete time specs, you convert them to continuous time specs. Here you design a filter and then convert this filter to a discrete time filter. So you go through this route, and there you need to, any transformation in from S domain is the Laplace domain. So usually filter is designed in Laplace domain. So from Laplace domain you convert your design, a transfer function h of s, into a transfer function h of z. So h of s, all the filter design packages, they make sure that all the poles are in left hand side S plane for a system to be stable. So the transformation will map all the poles here. If there are 4 poles, 4 poles will be mapped inside the unit circle, guaranteed. So the transformation should be such where all the poles should be mapped inside the unit circle. So pole on the, obviously if there is a pole on j omega axis, it will be on the unit circle, and so on. So we covered this, and this will ensure that a stable and a causal continuous time filter will result into a stable and a causal discrete time filter. So this will make, this transformation will ensure this point. Then we said there are usually three types. You may find others, but these are the 3 main categories of our analog domain IIR filters: Butterworth, Chebyshev, and elliptic filter. And the difference between these are that Butterworth is a monotonically decreasing function of omega. So it just goes like this. Okay? And it's very smooth frequency response. The Chebyshev type 1 allows ripple here, and type 2 allows ripple here, and elliptic allows ripple here and here, but within the specs. The important thing is that it never, so this is your spec, that you are allowing a tolerance here. Okay, So the tolerance here means that this is making full use of the tolerance. So the error is going up and down. And here it's just smoothly decaying to 0. So this is the difference. So we have seen, I showed you last time, that if you use MATLAB designing this is the most optimal. It'll just design a filter in minimum number of poles, elliptic filter. So, and this is what the order means. The order, as you keep increasing the order, n is the order, that how many poles. It'll be flatter. For example, this is for second order filter. Second order filter is where you have y of n minus 1 and y of n minus 2. So, and as you increase the order, the response gets flatter and sharper. Sharper, flatter here in the pass band and sharper here in the transition band. So as you keep increasing n, it gets flatter and sharper. Okay? So that's how once you give your specifications, the design tool will figure out that at what order filter will satisfy the design constraints. And we'll shortly see that how by tightening up the constraint means that the design tool will come back and ask a more complex filter. Here is another example of the response in relation to n. Okay, so as you can see, n is equal to 1 is this. N is equal to 1 is a and u of n. Y of n is equal to a, y of n minus 1 plus x of n. Just one pole gives you this filter. Okay, one pole gives you this filter, and 10 pole is this one. As you can see, a sharper and flatter. So that's what you want, a sharper and a flatter filter, but then you have to spend more in terms of the order of the filter. And this is what people tried. They tried using a mathematical formula which generate this curve. So this is an interesting mathematical relationship, 1 over 1 plus j omega over j omega. So in fact there is no j cancels out, but they're just keeping j omega for some reason, because it always says the frequency is in terms of j omega. So that's why they're putting j omega. But this is an interesting relationship, that once you start designing a Butterworth filter, you start with this expression. This is a frequency response of, and this is how mathematically it is represented. If you try to plot this, put a value of n here, put a value of omega, which is the cutoff frequency. Now start changing omega. If you do this exercise for a particular omega, this is then you will find that this thing will make this curve, okay, and which is very suitable for a low pass filter. So if somehow I can design something in electronics which results into this, means I can implement this filter, right? And this is electronics, analog electronics, that if somehow I can come up with a combination of capacitor resistors or from my perspective an HFS, okay, that if I replace, so I intend the filter design means you need to come up with an HFS, and the relationship between HFS and H of j omega is, as we know, the relationship between Z transform and the Fourier transform, that S is sigma plus j omega. So if you replace every S, you put sigma is equal to 0, then H of S become H of j omega. So this is a very simple relationship, that you have an S here, and once you put sigma 0, that S will become j omega. So means I will have a closed form expression for S, H of S. So once we say design means this. Once we say spec means this. In a log filter, design mean given H of S. Like in discrete domain, design mean H of Z. Because H of Z will do what? Will make a difference equation which you implement. In this, H of S will make a differential equation which you implement. Okay, H of S is basically a differential equation which you use in analog components to implement the differential equation. So this is the relationship. So this is how the Butterworth filter, this is the frequency response mathematical expression of a Butterworth filter. Similarly, people have come up with, after this, they have come up with others. The only difference between them is here you find few more factors, epsilon, t, and this is for the type 1 Chebyshev filter, okay, and this is the ripple it will cause, and this is type 2 Chebyshev filter. So same kind of relationship, the formula, but bit few more factors in it. So this is Chebyshev type 1. In type 1, the stop band is smoother. It's a monotonically decreasing function of frequency, but you have ripples here. So this is the magnified view of this portion, this here. Okay, so you see there are a lot of ripples in the passband. Similarly, this is type 2 where you have ripples here.
These ripples are in limit,
within limit. They got to be within limit.
They do not affect us.
No. So if they are not affecting us, why should I worry? So that is really the motivation, that if though they are ripples, but if they are not affecting me, why should I care? Okay, so why should not I go and implement a filter which costs me less? So they are within the limit for sure. Even here they are within the limit. Okay. So elliptic filter is where you have ripples here, ripples here. As you can see, it is 1 to 0.9. So all the ripples are between 1 to 0.9. No ripple outside this. Elliptic filter, and then so this is a comparison that given the limit, so gray is the forbidden region. You never want your frequency response to jump into this region and into this region. Okay, and you try designing filter. You say Butterworth will require order 44, whereas the Chebyshev type 1 only 14. Look at the difference. And 14, and elliptic will only take order 8. Okay, so these are the specs. 500 radians per second is omega pass. Omega stop is 600 radians per second. Ripple of 0.5 dB in pass band, and attenuation of 60 dB in the stop band. 60 dB means 1000 times lowers. So you want your unwanted frequencies to be slashed down by 1000 times. Okay, 60 dB means 1000 times down. So this is 1000 times down. So this is a comparison. Now comes the techniques. How do you go from h of s to h of c? So these are the two methods. One is called impulse invariance method, and the other one is called bilinear transformation. So these are the techniques of converting a transfer function h of s to a transfer function h of z, and the constraint is that a stable system here must result into a stable system here. All the poles in left hand side as plane must be inside the unit circle. So this is we want our method to obey the stability condition. So impulse invariance is very simple. In impulse invariance, the technique of impulse invariance is you design h of s. Okay, so that is what you get. And once you go filter design package, it'll give you h of s, a transfer function. You take its inverse Laplace transform. If you do that, what do you get? H of t. Okay, take its inverse Laplace transform, you get h of t. Now sample it. Once you sample it, you get h of n. Now you take its z transform, you get h of z. So this is a technique which is used in impulse invariance method. Okay, h of s, h of t. H of t, if you remember, h of s will have a corresponding h of j omega, which is the frequency response of the system. Okay, let's say if you remember correctly, this is, let's say, the h j omega, for example. This is h j omega. So once you discretize it, do you remember the steps we go through? You get a copy of it at every sampling frequency, right? So a copy of it at every omega of s, which is fine, we don't worry about this, because this will ultimately becomes 2 pi and this will become minus 2 pi. But what is the magnitude here? Sampling, it is 1 over t. We don't like this. We want it to be 1, because filter says 1. A 1 here must be 1 here. That is the reason you multiply with t here. Okay, a capital T into h of n to make sure that you get 1 as this. So you just scale this. Okay, t h of n. Another point, interesting point, is that remember you started with the specification in discrete domain, so it was discrete time. You convert the specification into, and this you are doing on a paper, so it's not actually you are doing it, means you are given, you need to design a filter in discrete time domain. You convert the specification into continuous time domain specification. Now you design, in fact, so design here for these specification, these are the specs conversion, this is the design. So you get a design in continuous time domain, and then you convert the design into discrete time domain. Okay, once you are going from here to here, the specs, you need to specify a capital T. So it's up to you, whatever you want. You can keep capital T whatever value you want. Okay, so then once you come back from continuous to discrete time, the sampling, through the sampling, you again need to specify T. So this T must be same as this T. If these are same two T's, then it does not really matter what the value of T is. For example, if I say 5 rupees is equal to $1, I don't mind if I'm converting dollar to rupees and rupees back to dollar. It will come back to be same, right? So if I'm going from discrete to continuous and continuous to discrete, the T will not matter. But important point is that you need to make sure you are keeping same T. Okay? Once you convert these specifications from small omega to capital omega, using capital omega T is equal to small omega. So the same T should be used once you convert, once you discretize this expression. And we'll see how to do this. But h of s into h of t into th of n, and this will give you h of c. And these are the steps you go through to design an IIR filter using impulse invariance method. So this is the idea is simple. H of n is a sample and scale version of the continuous filter h of t. So t into h continuous, nt is the sampled version. H of t, every sample is replaced by nt. If hcj omega band limited, one can simply sample it. The shape of the frequency response we know, small omega is equal to, so small omega is equal to capital omega into t, so capital omega is small omega into t. Saying this, it is scaling of the frequency axis, and we know it is scaling of the frequency axis. Once you do, you make copies, but it is important that it should be band limited. If it is not band limited, then the same thing will happen. What? Alias. So this is the problem with the impulse invariance technique, that mathematically it will alias. If it is not band limited, it will alias. Okay, so it will, maybe your analog filter, maybe it will be meeting all the specs, but once you discretize it, it may or may not meet specs. I'll show you that it, because of the aliasing, it may not meet specs because of the aliasing effect. So this is a problem with the impulse invariance method, that this may or may not. So usually bilinear transformation is used. So I'll shortly do an example, and you'll be able to follow through. In practice, hcj omega will not be band limited. Aliasing, that the choice of t cannot prevent. And remember, t will not help you. You cannot say, okay, I'll sample it fast enough. There is no fast enough, because t is just a superficial variable which you are going in a loop. So t will not help. So t is not going to help. T will not help. So design technique is this. First of all, you have an h of s. Then, as we do in Z transform, to find h of t, you need to make partial fraction of h of s. Then you take its inverse Laplace transform each pole into its transform equivalent, and then combine the terms into a single polynomial. I'll show you this. So this is the effect of aliasing. Let's say you are designing a filter, and so Butterworth helps, because Butterworth are smoother, so they just go down. Okay, smoothly decaying and dying. So it is a 24th order Butterworth filter in analog domain. Once you make copies of it a copy here, a copy here, a copy here at every omega s. So still it satisfies. So discrete version also satisfies, right? But on the other hand, if you use Chebyshev type 1, you may be okay, right? Because smoother here. But this is for type 2. This meets specifications. Ripples here meet specifications. Once you but make copies, the discrete no longer meets specifications, okay, because of the aliasing effect. There will be aliasing. So it's no more meet specifications, means that it may be misleading for you to do this, because you do this, you are happy with the analog filter, where you convert it to a discrete time filter and it won't meet specifications. And specifications are important, very important, because that's why you specify. You can't say, okay, I don't mind if it is instead of minus 60 dB, it is minus 40 dB. No, it matters a lot, because all your algorithms are assuming, because this is out of band noise, which will get into everything you are doing. Okay, so the specifications are important. So this is elliptic again. You can see this meets specification, but this no longer meets specifications, okay, because of aliasing. This is impulse invariance method. The method is simple, that you have a transfer function hc of s, you make partial fraction expansion, convert all as we do in Z transform. Everything will s minus sk, and this here is the pole sk, and usually sk is negative because got to be on left hand side as plane. Then its inverse Laplace transform is this exponential skt. I think इसको नमाज के बाद कर लेते हैं. ये अज़ान ही हो रही है ना? चल do it after. Okay, so this is the impulse invariance method, in which you start with a transfer function in analog domain, that is hc of s. Then you make its partial fraction. So there's several of these terms, ak divided by s minus sk. Okay. Take its inverse Laplace transform. So inverse Laplace transform of s minus alpha is exponential alpha of t u of t. Okay. This is the inverse Laplace transform. As in discrete case, we have several exponential a and u of n. In analog domain, you have several exponential alpha of t u of t. So that is the difference. So you get exponential alpha of t u of t. So several of these for every pole. Every pole will contribute an exponential in the summation. Exponential skt. Sk is the location of the pole. Okay. So for every pole you get an exponential. So this summation ak exponential skt ut. Now we know the method. The procedure is, now you discretize it. You make h of n, but h of n also comes with an extra t. This is for the scaling. Okay. So t ak comes as is. Okay, and for t you replace it by n capital T, and ut means only it is for positive values of t, so you write h of n. Okay, so these are the steps. If let's say if I assume just a single pole system, okay, so let's say if I ask you to convert a transfer function with a pole at -5 into a discrete time system, a pole here in S domain. This is sigma, this is j omega. So you say h of s is 1 over s plus 5, because pole is at -5. Okay, or minus 5, you can write it like that. Right? So h of t is exponential minus 5t u of t. This is the inverse Laplace transform. is an decaying exponential. A minus always means a decaying exponential. A plus means a rising exponential. So this, and now you discretize it. You say h of n is equal to t. So this t is an extra, comes into here, minus 5 n of t u of n, and this can be written as t exponential minus 5 capital T raised to the power n u of n, right? This is now h of n. You take its z transform. This is alpha of n. So what is the z transform of this expression? T is 1 minus x e exponential minus 5t z inverse. Okay, this negative value means always less than 1. Okay, and exponential of minus means always less than 1. What does it mean then? That this is always less than 1. So what is this in z domain? It is what? It is a pole which is inside the, always going. If this is negative here, if this is negative, it will guarantee that this will always be inside the unit circle. So the relationship is simple, that a pole in S domain will be an exponential of that pole in Z domain. That is the relationship. A pole here will be an exponential of minus 5 into t. You can keep t is equal to 1 because t, remember, does not really matter. So a pole there is an exponential of the pole in Z domain. So this is the relationship. Once you convert from here to here, you can directly convert instead of going through all this. Looking at this, you know it is 1 minus exponential minus 5 Z inverse. So this is the answer from HC of S to HZ. And then you can actually plot the Z transform, the pole location in. So guaranteed I'll be inside the unit circle if a stable pole in S domain will be transformed into something in the Z domain. So as you can see, there are multiple of these S of k. You discretize them into a k exponential, replace t by n of t, u of n. You take its Z transform, then you have all these poles here, exponential sk capital T. Right? Every pole in Sk will be a pole in exponential Sk in Z domain. So this is the relationship. No matter how you design HC of S, but you get an HC of S and then you do this. This is an example that how do you actually design HC of S. Okay, this is for the Butterworth case. You start with this mathematical expression which I showed you earlier, that this is a very good mathematical expression because it generates a monotonically decreasing function of the variable which is omega. If you increase the value of capital N, it will be sharper and flatter and sharper. So it's a very good function. So you start from here and you know that this is magnitude square. This is magnitude square of a complex number is a complex number multiplied by its conjugate, gives you the magnitude, right? Magnitude square is the complex number multiplied by its conjugate, give you the magnitude square function. So HC of j omega multiplied by HC conjugate j omega. How to get HC conjugate j omega? Replace every j by minus j, so you can write it like this. HC j omega HC. Now we are trying to come up from here, we are trying to come up with HC of S. If from this expression, how do you get HC of S? Okay, this is again a very old technique. If any one of you has taken a course in analog filter design, you learn all these techniques there. Right? So you say, okay, H of S. So this, now I know that there is a relationship between S and j omega, and that is S is equal to sigma plus j omega. Okay, so I, instead of writing this, I write it sigma plus j omega, sigma minus j omega. Okay, so sigma plus j omega is, I write it as S, and this I write it as minus S. H of S, H of minus S, and for j omega I write S, and omega c is a constant. It is the cutoff frequency. So this expression, the magnitude square expression, can be written like this expression. I am not interested in H of minus S. I'm only interested in h of s. But there is a relationship. If I say, for example, h of x, any function of x, is 1 over x minus 5. Ji? Sigma is in S domain the x-axis and j omega is the in S domain. Like in Z domain you have r and exponential j omega. Okay?
Sigma 0 also
Sigma 0 means j omega axis, the Fourier transform. Okay? Like in Z domain, r is equal to 1 is the unit circle, which is the Fourier transform. The same relationship, and I would really suggest that you must go back and revise the Laplace transform, okay, so that you know these things. So just a quick review of Laplace transform will help. Just not a lot, but at least going through this, the relationship between S and j omega, stability and all that, and inverse Laplace transform. So this is h of s, h of minus s. Okay, so h of s and h of minus s is same expression, 1 plus s over j omega c 2 raised to the power n. But remember, I'm only interested in this. I'm not interested in h of minus s because I want h of minus s, h of s. Okay. This expression has, it is the variable s. Okay, once you write an expression like I say 1 plus x square, how many roots do I have in 1 plus x square? 2. What are they? No. Plus minus j. So 2 roots. Okay. If I put 3 here, then what? You have 3 roots. And where are those 3 roots? No. It is on the, look, if you have 2, you have the roots here. If you have only 1, if I start this, 1 plus x is equal to 0. How many roots do you have? 1. Where? At minus 1. Then you say x square, you will have 2 roots. If I say cube, there will be 3 roots. If I say 4, there will be 4 roots. If I say 5, there will be 5 roots. They will be equally distributed on this unit circle. If I say 1 plus x square, x cube, it means there are 3 of them. Once I say 1 plus x4, there will be 4 of them. And similarly, there'll be we say that nth root of unity. Again, in maths, if you go and try to revise that, it's nth root of unity. Means if I write an expression like this, 1 plus s, and I try to find the roots of the polynomial, this, so 1 goes on this side, it becomes minus 1. Then you have minus 1 raised to the power, right, 1 over 2n, then this j omega c comes here. Okay, so these are the roots. For this minus 1, 1 over 2n means that it has 2n roots on the unit circle. Okay, minus 1 square means, square root means 1 over 2 means 2 roots. And where are they? J and minus j. If you say 1 over 3, 3 roots. 1 over 4? 4 roots. 1 over 5, 5 roots. 6 roots, 7 roots. And they'll be equally placed. So if this means, and j is 2 pi. So this pi by 2 is for this j. And minus 1 means that there are these roots. First root is at pi over 2n. And then equally placed. The pi is divided into n parts. So 2 pi over n. Then you move pi over n, pi over n, pi over n, pi over n, pi over n. This will, by putting different values of k, will give you all the roots of this polynomial. जी देखिए, j is pi by 2. Exponential j is exponential j pi by 2 because the cosine of pi by 2 plus j sine of pi by 2. So pi by 2 sine of pi by 2 is 1. So that's why you just bring it up, and this is an initial. So initially you give a pi by 2, but you can actually, knowing this, you can plot all the roots of this whole expression, h of s, h of minus s. Okay, and this is again the procedure people adopt to design a Butterworth filter. That you start, this is the expression, you come up with these are the poles. Just remember these are the poles. Okay, and just remember this formula. If you know capital N, you can actually plot. If capital N is 0, it means there is n is equal to if capital N is equal to 1, there is only 2 roots total for this, one for h of s, one for h of minus s. So using this you can actually now plot. Okay, so once you plot, this is the, now this is no more a unit circle, this is a circle with radius omega c. Remember r exponential j theta, this is this radius, and this is the angle where you place the roots. So the roots are placed on omega c circle, equally placed using this formula, and they look like this. If they are n is equal to 3, then for h of s and h of minus s there will be total 6 roots. 3 for h of s, 3 for h of minus s. So these are the 6 roots. Okay, I always pick these because left hand side as plane means stable system. So I always pick these for h of s and I leave these for h of minus s. They will always be placed on the unit circle. I always pick the one which are on the left hand because I have to distribute them. Half of them should go to h of s and the other conjugate should go to h of minus s. If I want to, I can say all these are h of s and h of minus s, it will still satisfy the equation, but the resultant system will not be a stable system. So you pick the one which gives you a stable system. Okay, so if there are 4, then you will have 1, 2, 3, 4, 5, 6, 7, 8. And how do you compute this? It's simple, go to this formula. Okay, go to this formula, put here n is equal to, if 3 it is 3, n is equal to 3, k is equal to 0. K is equal to 0 means 0, the first root, I am plotting first root. It is pi by 2 plus pi by 6. So pi by 2 plus pi by 6 is pi by 2 plus pi by 6. This is the place. This is you plot the first one. Okay, now you put k is equal to 1. Once you put k is equal to 1, here you need to move by another pi by 3. So from there you always move pi by 3, pi by 3, pi by 3, which is 60 degrees. So if you look at this, this is from here, it is 30 degrees plus 60 degrees, is total of 90 degrees. So from here you plot this, another 60 degrees, another 60 degrees, another 60 degrees, another 60 degrees. So that's what you do. Similarly here, pi by 2 plus pi by 8. First is simple, pi by 2 plus pi by 8, then pi by 4, pi by 4, pi by 4, pi by 4, pi by 4. So you can easily plot the first one is always pi by 2 plus pi over capital N. And then every one is at pi over 2n and then pi over n, pi over n, pi over n. So this way you plot the roots, and then you pick, in this case you pick these 3s, in this case you pick these 4s. Now the real question is, how do you know omega of c? How do you know n? These are the only 2 design parameters while designing a Butterworth filter. In this, because you only need to know the location of poles. If you look at the formula, what do you really need to know the location of poles? This is the formula for Butterworth filter design. Doing all the maths here, and if you remember, if you know the pole, then a pole in Z domain is simple. It is exponential of Sk. That is the very simple relationship. Find a pole in S domain, map this pole in Z domain by just this formula. Okay, so only the design parameter is that omega of c need to be known and n need to be known. If you know omega c and n, you are done. Okay, so in Butterworth filter you try to figure out these 2 design parameters. And how do you do this? From the design specifications. Let's see how actually you compute n and omega c. Rest is simple problem to solve. So you know the design parameters. So this is same. This slide shows you the same thing, that you have poles here, this is the location of poles, and once you know the poles, you write them like this. They'll be conjugate in pair, and then you write inverse. So here is an example. Usually, as we know, you will be given design specifications. Design specifications are in terms of small omega, because I want to design a discrete time system. I give you a specification that I want this digital filter, but I say I want an IAR filter. I say I want a filter where the frequency response from 0 to 0.2 pi should remain between 0.89125 to 1. So this is my pass band ripples, that it should be within this range. It can ripple, but in Butterworth it does not. Okay, in Butterworth it'll do a monotonically decreasing, and I also know the monotonically decreasing means that it will only pass through this point. If it'll start, it'll go pass through this point. This is my limit. At omega p, it will pass through this point. Then let me put here. So these specifications are in terms of, I want it should remain between 1 and 0.89 and whatever until 0.2 pi. This is design specification. Then I say in 0.3 pi it should never go above 0.001, for example. So I know the design specification. Knowing this, I can plot, at least I know 2 points or 3 points in the Butterworth. Butterworth is monotonically decreasing function. So I know for sure that any filter and designed to the specification will pass through this point and this point. Any filter which is going above this point is what? Is an over design. It will be a higher order filter, flatter. If anything which is flatter than this means it will take more, capital N will be bigger. Anything which will go below this, it is under design, it is not meeting specs. So a filter which meets specs is guaranteed to pass from this point and this point. So I know 2 points, and this is the plot of my HCJ omega magnitude square. This is the plot of HCJ omega magnitude square, which is the formula. I know it is 1 over 1 plus j omega c. This is the formula. Okay. So there are 2 points and 2 unknowns. N is unknown and omega c is unknown. I know that if I know 2 points and there are 2 unknowns, I can solve the equation. Okay. For example, if I say a plus b plus 5 or xy kar le, means ax plus bx square, whatever is this, and I have an equation with 2 unknowns. Y is equal to mx plus c. Jis tarah this equation has 2 unknown. One is m, the other one is c. If I know 2 points on this line, by putting this value of x, for this x this is y, and for this x this is y, I can generate 2 equations, solve them simultaneously, and I can easily get the value of m and c, and we know this. So means to solve, remember these are the only 2 design parameters. You need to figure out n, you need to figure out omega c, then you know the formula of all the poles. If you know n, you know omega c, you can plot exact location of the poles, and that is what it matters. So for this, now it is very trivial problem to solve. First you write at 0.89, this is your omega p and this is your omega stop. You need to change it to capital omega p, which is equal to this, and capital omega stop into t, because you need to convert your specifications into analog domain specification, and converting means only you need to change omega axis. If you keep t is equal to 1, what will happen? Same. So usually you say t is equal to 1. t is equal to 1 means small omega will be capital omega, small omega will be capital. So now what you need to do is you say, okay, at 0.2 pi, so put omega is equal to 0.2 pi. And what is HCJ omega? At 0.2 pi, what is the value of 0.89? Here you put, this is one equation. Okay. Now what you do is you bring this on this side, write it in an equation form, take log of this so that 2n comes in the denominator and make an equation. How do you get the other equation, second equation? It is at 0.3, 0.001. So it is 0.001 and here is 0.3 pi. If you do this, you have two equations, two unknown, solve the two equations, find out n and omega c. You know n and omega c, you go plot all the poles, you know all the poles, you know all the poles in the z domain, so you have solved the design problem. Okay, so here is, as we know, it's monotonically decreasing. Anything which goes below means under design, anything which goes up means over design. So we want this curve which exactly passes through this and this. So you put at 0.2 pi, value is this square, so this is one equation, and at 0.3 pi value is this, not 0.0001, it's 0.17, whatever, it is this. So now you cross multiply. If you cross multiply, you get this expression, okay, and then take the log so that 2n comes in the denominator. You have one equation which is this, and then you have another equation, solve them simultaneously, you get n is equal to 5.9. okay, n is equal to approximately, but it got to be an integer. If it is even 5.1, you need to say it is 6, because 5.1, if you go down to 5, it will be under design, but you don't mind designing it, making an over design instead of an under design. You say, okay, you will always take the ceiling which is 6, put that will give you a value of omega c. Okay, so get n, round it, get the value of omega c, and once for this value of omega c, draw a circle. Okay, how many? So can you tell me, n is equal to 6, where will be the first pole? How many will be there? N is equal to 6, 12. Where will be the first one? Pi over pi by 2 plus pi by 12. Pi by, so it will be, what is the circle? Circle is, so the circle is 0.7032. The first pole will be somewhere pi by 12, and then there will be 6 of them here. Okay, 6 of them, and then 6 on the other side, and you don't care about those. So here are the, okay, so here are all the poles. Okay, here are all the poles, and then so there is perhaps, okay, so now you take only these 6, 1, 2, 3, 4, 5, 6. So take these 6, those 6, combining the pairs together, this and this, this and this, this and this, will make 3 second degree polynomial. Usually this number, it becomes appears in the numerator instead of 1. It is because of this omega c. It is omega c perhaps raised to the power 12 or 6. Okay, so this constant will always be a constant, which is the constant which is appearing in the denominator. Other than this, these are all the poles, 6 of the poles. Okay, if you and if I give you, let's say, 2 poles, one is here, let's say this pole is at minus 0.5 plus 3j or whatever, it got to be, yeah, and this one is minus 0.5 minus 2j, for example. Okay, so how will you write the transfer function HC of S? HC of S will be S minus S, or you can say minus this pole into S minus this pole, right? S minus this pole and S minus this pole. Now you multiply S square, okay, and then you multiply this with this and this with this. The imaginary will cancel out, it will be only real one. Multiply this and this, so you get a second degree polynomial, which is shown here. So for two of these, you get this. And now we know, once you have all the poles, then you can plot by keeping t is equal to 1. These are the partial fraction, expansion and all that, but end of the day you get the same poles but on exponential of sk on the unit circle. So this is the process you go through to design a Butterworth filter. So here is where you have SG of S has 6 poles, okay, and this is translated into this in H of Z. So every S of K is appearing here. The same polynomial expansion, the binomial expansion, they're the same constants. You need not to even change them. And then you combine, so you can keep t is equal to 1 and you translate an HC of S into H of Z, which is written here. This is usually, we prefer second degree polynomials, so these are second degree polynomials because there you don't have to deal with complex numbers. And remember, a second degree polynomial is a difference equation, so this is as if you are implementing them in parallel, 3 of them in parallel. 3 second order system in parallel will make a 6 order system. It's up to you. You can just implement one long difference equation, but usually it is preferred to break a difference equation down into second order section. Okay, that's what the MATLAB does for you. Always gives you second order section. So better second order sections. So this is the design. So let me quickly recap that how you design. You start with the specifications. The specifications are given in discrete domain. You convert these specifications to continuous domain, and the only thing you need to convert is the small omega into capital omega. But if you keep capital T is equal to 1, then small omega is capital omega, so the same specifications. Then you write this, the transfer function. So go back. Here is that. Yeah. So then you have 2 points. You solve this for 2 points. Make 2 equations. Solve the 2 equations. Okay. First, always find n. Okay, because then you need to round this n, and then put the value of n here. Okay, that'll give you the omega c. Take the omega c and plot all the poles. Convert poles into H of S and convert them to H of C. So this is the impulse invariance technique. The problem with impulse invariance, I have already discussed that the problem with inverse impulse invariance is like a filter which is stable in which meets specification in continuous domain may not meet specification in discrete domain. Okay, so that is the reason this is usually avoided. And the MATLAB default is that it uses bilinear transformation. What a bilinear transformation does is, it is a non-linear mapping. The mapping which is shown to you is where small omega is equal to capital omega into t, and capital omega is small omega over t. If t is equal to 1, then it remains as is. There is another specification, another translation, which will, as you move away from this axis, it will change the shape of the curve. It will make it go down like this. I'll make sure that you are still meeting specification, but it will change the shape of the curve. The transformation will change non-linearly, change the shape of the curve so that it just ends. It never goes, So that type of transformation is required. Not this is a linear, it's a straight line. This is a linear translation. Means no translation almost if capital T is 0. Okay, so you want a translation which is something like this. This really works well, though it is non-linear, but I don't care, and I'll tell you why I don't care. As you can see, there is this relationship. Capital omega is 2 by capital T tangent omega over 2, and I'll tell you why. Okay, so small omega is 2 tangent inverse capital omega T over 2. This is a transformation. No matter what value of omega you put, it will make, once the omega tends to infinity, this relationship will make omega goes to pi. Okay, so let me now try to explain what it does. It says I don't like linear translations, so if I have a graph like this, okay, there is minus infinity and positive infinity. I want a translation which will map this minus infinity to minus pi and positive infinity to positive pi. Okay, and then it will just wrap, compress and put this response, making sure that it never goes beyond minus pi and pi. Now if you replicate this, there will be no aliasing for sure, because you have cut it down, you have changed it, and it never goes. So minus infinity and infinity will be mapped in small omega domain into minus pi and pi, so that once you make replicas, it will never overlap, no aliasing. But the as we know, the shortcoming is that you are changing the shape of the curve, of course, but as long as it meets your specifications, you don't care. Okay, so this is what bilinear transformation is, that it is called warping, that you use this curve, which is this curve. Here is your capital omega and here is your small omega. Okay, as capital omega goes to infinity, the small omega will never go cross pi. It's a tangent curve basically. As you know, the tangent curve looks like this, right? It never goes beyond these two lines. So this will make sure that for every value of omega, so this is how you translate. You say, okay, for this value of omega, HC of j omega, you pick an omega and draw it on the small omega axis. It becomes this value becomes this value becomes this. If you do that, no matter where you go, you never cross pi and minus pi. So your discrete spectrum is guaranteed to be fit into minus pi and pi. And so let's now see that what is this transformation. In this transformation, S, and remember there you started with HC of S and you said you will only convert it as to H of T, and then you will discretize it and you will take Z transform. Okay, these are the steps you went through to design an IR filter. In bilinear transformation, you say, no, I will replace an S with this complex function. It is 2 over capital T, 1 minus Z inverse, 1 plus Z inverse. So every S is replaced by this expression. Okay, and we only need to prove that this expression means what I showed you in terms of j omega and small omega. We'll shortly find that out. And also we need to make sure that this expression will ensure that this left hand side S plane is mapped inside the unit circle, so that stability there guarantees stability. So these are the two things which you need to make sure that it still happens. So how to prove this? And in this capital T, you can assume capital T is equal to 2, so that 2 cancels out with 2. Okay, this is 1 minus Z inverse, 1 plus Z inverse. For example, the last time we did an example, S plus 5. Okay, and we said it is very simple. In Z domain, what you do is it is 1 over S minus exponential minus 5 Z inverse. So this was the expression. This was the expression in H of Z. Remember? So we said it is simple. A pole here will be a pole at exponential minus 5. So, but in this case, you replace this S by 1 minus Z inverse 1 plus Z inverse. So this is the transformation. that an S is replaced by, and still I want to make sure that this transformation will not disturb the stability. Okay, so if I do this, 1 plus Z inverse gets in the numerator, and what do you get in the denominator? 1 minus Z inverse plus 5 Z inverse. Okay, so what is this equal to? This is a 0 at minus 1. Okay, this is a 0. I really don't care about 0, so I'm more focused towards the poles. So 5 plus 1 is 6, and 5 minus 1 is plus 4 Z inverse. Okay, so now what I do is I take 6 as common to make it in that form. So 6, if I take 6 common, what do I get here? 1, and what do I get here? Is it less than 1? It is less than 1. Where is it? At 2 by 3. At minus 2 by 3 in fact. So a pole here will result into a pole inside the unit circle guaranteed at minus 2 by 3.
So they don't care where the pole is as long as it is inside?
Yes, we don't care where the pole is as long as it is inside the unit circle, at least for the stability. And the transformation will make sure that the pole is correctly placed to meet the specifications. So still give you an h exponential j omega which meets the specifications. Okay, so this is the job of the transformation. So transformation is ensuring that the pole is inside the unit circle, guaranteed. Okay, and we'll generalize this. This is just for this example, and we know that a pole in S will map to only one pole in Z. So 1 degree will result in a 1 degree in the Z domain. So this is, if you go back, you see this, we started with that you have S is equal to 2 over capital T, 1 minus Z inverse over. Okay, now I'm just to demonstrate that this in fact is the same transformation which we started. We said we need a non-linear transformation. Simple, you replace S by sigma plus j omega and Z inverse by R exponential j omega, and we know, we'll also conclude this, that in fact the j omega, if you put sigma is equal to 0, it means on Z domain you are on the unit circle. We'll shortly prove this. So if I put sigma 0, it means R is equal to 1, because j omega axis is the unit circle. If I do that, now it is simple. Do the same trick. Exponential j omega is exponential, put it exponential j omega over 2 and exponential. Remember the trick, you do this and 1 should be replaced by exponential minus j omega over 2 into exponential j omega over 2. So you do that, so it will result into sine omega over 2 cosine omega over 2, and this will result into tangent omega over 2. So remember, this is from where we started, that this is in fact a non-linear translation of small omega into capital omega or capital omega into small omega. Okay, so this is, and you can go in reverse direction. Starting from here you make this, from here you make this, from here you say go to the S. So the translation is this, and this is a curve which really helps us out to, and this is where you can prove as a matter of fact that generalized proof. Generalized proof is that if you have a pole in left hand side as plane, it guarantees a pole inside the unit circle in Z domain. How? Starting from here, this is the relationship between Z and S. Z is equal to 1 plus S over 1 minus S, and you know what an S is? It is sigma plus j omega. Okay, so let's say this is the location of the pole, sigma plus j omega. So S is replaced by sigma naught plus j omega naught. So S is replaced by sigma naught plus j omega naught. For negative sign, it negative here and negative here. Okay, so this is what you get. Okay, if you take its magnitude square, the magnitude square is real magnitude square plus imaginary magnitude square, real magnitude square plus imaginary magnitude square. This is the magnitude square. Now sigma, if sigma is negative, okay, so this will be negative something and this will be positive something. So 1 minus negative something will be less than 1, and 1 minus positive something will be greater than 1. Sigma naught is same. So this is not going to affect the value. a smaller thing divided by a bigger will always be less than 1. So this is a proof that if sigma is negative, this transformation will always result into a value of z which is less than 1. It will always inside the unit circle, guaranteed. Okay, sigma negative means inside the unit circle. So this is the bilinear translation which says that unit circle is the j omega axis and this whole plane will be mapped inside the unit circle, and this is really the effect of warping, that in fact this is that curve. This is your h c of j omega. So as I mentioned earlier that if you are computing, go to a value of omega, find out the hcj omega, and now translate it into small value of omega. It is guaranteed this whole thing will be between 0 and minus pi and pi, or if so this whole thing is guaranteed. If it is going from 0 to infinity, it is guaranteed that this whole thing will run from 0 to pi. If it is minus 0 to infinity, guaranteed. So but what is the effect? The effect is as you move towards these frequencies, okay, the curve is like this, so all these frequencies will map to, so this big region will map to this very small region. This is non-linear mapping. Okay, here it is almost linear, but as you move away it is non-linear, and this will cause the response. Okay, this is a very good figure which shows you the effect of this curve. Okay, because of a slope, this portion will look bigger here, or this portion will be compressed, but because of this, if it meets specifications here, it is guaranteed that it will also meet specifications here, guaranteed, because you are taking a value and just plotting it here, taking an omega p, convert it into small omega p and plot. This is how you plot. You take value of 0 is 1, you say in small omega value of 0 is 1, for example. Now you take another value at capital omega p, you say capital omega p is, let's say, 0.9. okay, you take this capital omega, convert it into small omega. How? Using that formula, which is basically this curve. You find out a small omega, go to that small omega and say at this small omega value is 0.9. okay, then you again move, so you keep moving on capital omega, noting the values, converting capital omega into small omegas, coming down, taking small omegas and plotting the same values here. So it will guarantee that meeting specs here means meeting specs here. And also remember that in fact you started your design from here, that these are your specifications in discrete domain. You use the same curve to convert small omegas into capital omegas. So basically you start from here, your specs, you convert your specs here, then you design and convert your design here. And this is what is happening in frequency domain. But for you, what matters is that it's very simple to design. Number one, all you have to know is that every S to be replaced by 2 by capital T, 1 minus plus minus minus, okay, perhaps. So this is all you need to know, that every S go and replace it by, let me make sure it is yeah. So every Z is replaced by this. So this is, otherwise it is very simple to learn, and this is what will happen in frequency domain. I'll ensure stability, it'll ensure everything. So if I show you the same example which we did earlier, so what do you get? You get poles and you get an HC of S. Okay? So once you do the Butterworth filter design, The only difference here is the same design example. Now to convert the 0.2 pi, this frequency, into capital omega, you will not use small omega is equal to capital omega into t. No. Now you use the formula which says small omega or capital omega is equal to 2 by t tangent small omega over 2 or something. Yeah. So this is what you need to use. Okay. So the frequencies needs to be converted using this, or both the frequencies. Okay. So this is the only difference. First, once you are converting specs from discrete domain to analog domain, you need to use the same transformation. Okay. Now you start your design. Okay. Design you start exactly same. You say, okay, this is my specs, but only now this will no more be 0.2 pi. This will be some other value. This will no more be 0.3 pi. This will be some other value. But other than that, everything is same. That you need a monotonically decreasing function of frequency. So you know this point, you know this point. So this point is same, which is 0.89, but this value is different. This point again is same. It is 0.1778, but this frequency is different. Put it in the equation. Equation is same. The Butterworth design, still you find that it requires 5.3. Okay, it says 5.3, but whether it is 5, 5.1, 5.3, 5.1, anything which is greater than 5 means 6. 6 means the same thing. Now omega c is this, so you design 6 poles and then find an h of s and take that h of s to h of c. And you, if you want to, you can exactly in fact figure out that how a pole will be transformed to this. And remember, I did that if you know a pole in S domain, S plus Sk for example, or S minus Sk, whatever you just go through, S replace S by 1 minus Z inverse, 1 plus Z inverse. Go through and you can exactly figure out a pole in S domain will be placed here in the Z domain by just doing a little bit of mathematical manipulation, which we did. Okay, I think it is 1 minus Sk over 1 plus Sk or something, 1 plus Sk or 1 minus Sk. So this will be the location of the pole. So you can find the location of the pole as well. Ji.
In the last domain or S domain, all the poles will be placed on that omega c circle?
Ji. Yes, guaranteed. All the poles will be on omega c circle, something like this. Okay? And that's why once you design Butterworth filter, you will find even in Z domain, the poles are placed on a circle. Even if you go in MATLAB, use Butterworth filter, you will find all the poles are placed on a curve. That is because of the poles here are on a circle, and once you translate, they appear something like this. Okay? So, but this circle has nothing to do with the unit circle in Z domain. This is an S domain. Okay? So I think this is where I conclude, and tomorrow we'll try to cover the FIR filter, and next week onward we'll start with the other book, which is statistical signal